Hello, my name is McGuire Hodson, and this is my lab report for Lab 4, Magnetic Braking with Faraday. The purpose of this lab was to observe the physical behavior of a magnet falling through a conductive tube, and to replicate that behavior computationally using VPython. This lab is based on Faraday's law, which states that E equals negative d phi b over dt, and it is also based on Lenz's law, which is the negative part of that equation, which says that the induced current will flow in a direction that opposes the change in magnetic flux that caused it. The computational model used successfully predicts terminal velocity and reproduces the magnetic braking effect that was observed experimentally. To carry out this experiment, a tube with a length of 0.31 meters, aluminum foil with a width of 0.05 meters, and a radius of 0.02 meters, and a 0.025 kilogram magnet with a dipole moment calculated to be 3.15 were used. The magnet was dropped into the aluminum foil tube, and the time for it to exit was measured. This was repeated 4 more times to improve precision. In this experiment, the system being analyzed is the bar magnet, while the surroundings are the aluminum foil tube that generate current, and the earth, which provides the gravitational force. And so this is a picture of the experiment. The computational model was set up based on the experiment, so the tube length was set to 0.31 meters, the inner radius was set to 0.02 meters, and the foil width to 0.05 meters. The magnetic dipole field equation was implemented using the vector form of the Biot-Savart law, and the flux derivative was used based on the changing position and velocity of the magnet. Additionally, Newton's second law was applied to update the velocity and position of the bar magnet using the velocity and position update formulas. Faraday's law and Lenz's law were applied to the computational model to calculate the current in each ring and to compute the magnetic force from the rings back on the magnet. The constant used are G, which is 9.81, Coulomb's constant at 1 times 10 to the negative 7, and the resistivity of aluminum at 2.65 times 10 to the negative 8 ohm meters. And these are 2 pictures showing the relevant code in the computational model. So, for the results, the experiment yielded an average fall time of 0.994 seconds for the magnet, which is significantly slower than what would be expected with no induced currents, which would be about 0.3 seconds. The delay is due to electromagnetic damping, a magnetic braking force produced by the induced currents in the conductive tube. In the velocity versus time plot generated by the computational model, 3 main phases are observed. The first one is a rapid drop in velocity when F-grav is significantly greater than F-mag. The second one is a flat terminal velocity region where F-grav is about equal to F-mag. And the final phase is a final acceleration as the magnet exits and F-mag drops off significantly. In the simulation, the red color indicates counterclockwise current and the blue represents clockwise current, these both being as viewed from above. So this is the graph. It shows that the average time in the tube was 0.994 seconds. And this is an image of the magnet falling through the aluminum foil tube with the currents indicated. So if the resistivity of the aluminum tube were reduced to near 0, the induced currents in each ring would be much larger. Therefore, the magnetic braking force would increase significantly and the magnet would slow down much more quickly. If holes or slots were cut into the aluminum tube, they would interrupt the paths of the induced currents in the rings. Since eddy currents require closed loop paths, cutting the tube would reduce or even eliminate current in affected sections. While the results of this experiment mostly match what was predicted, some possible sources of error include video timing uncertainty, air resistance, and an imprecise measure of the magnetic dipole moment back in Lab 2. Overall, this lab effectively demonstrated how Faraday's law and Lenz's law apply to real magnets that go through aluminum tubes. So that's all. Thank you for watching.